We talked about relations and functions. Now let's talk about inverse relations. See, pretty much every operation in mathematics has an inverse, something that will undo it. Multiplication has division, addition has subtraction, logging has exponentials, and so on. What happens is it returns those dependent variables back to the independent ones. I've got these two sets here, A and B. This is the relationship y equals x squared. So all my x values have been squared to get the y value. To get it back to the original set, I would apply y equals plus or minus the square root of x. If I apply that to each of these values, then I'll get back to the original values that I started with. And so that's what an inverse should do. So A and C are essentially the same set, they're equal sets. If you want to work out what it is, you simply swap the pronumerals around and then make y the subject. So our one I just did, we had y equals x squared. If I swap the pronumerals around, I get x equals y squared, make y the subject, y is plus or minus root x. That gives us our inverse relation. What ends up happening then, because we're basically swapping the x and y's, the domain of the relation will be the range of the inverse relation, and vice versa. So the range of the relation will be the domain of the inverse relation. Now, if you were to draw both of them on the same number plane, they are reflections of each other, but in the line y equals x, because we're swapping the x and the y's around. So any point on the line y equals x would stay there, because we're swapping it around, but then all the other ones will reflect. So if I wanted to draw the inverse relation of this shape, then what I could do is draw in the line y equals x, and I just have to reflect every point through that line. Now we pick sensible points. So for instance, I would pick, say, this x-intercept. Now to reflect, you'd have to go at right angles to the axis, and then obviously the same distance the other way, and that x-intercept now becomes a y-intercept. I could do the same with those two. And there are other important points, maybe these turning points. That would be good ones to plot, and as many as I need to get the eventual shape. And once we've got the two shapes there, we can see, if you turn your head 45 degrees, oh yeah, look at that. They are a mirror image of each other. Well, that brings us up to this idea of inverse functions then. So that was inverse relations. What's an inverse function? Has to have a one-to-one relationship. One-to-one relationship. Now, if that's true, then the inverse relation has a better name. We call it an inverse function. How do you test for it? Well, it needs to satisfy, first of all, the vertical line test. So it's a function to begin with. But then also the horizontal line test tells me that the inverse will also be a function. And that was also our definition, if you remember, for one-to-one. Satisfied both tests. Another way is, if you want to do it algebraically, is work out what that inverse relation is. Now, if it's unique, then it's an inverse function. What do I mean by that? Here's the y equals x squared that we talked about. Visually, oh yeah, satisfies the vertical line test. So first criteria, it is a function. Horizontal, no. Doesn't pass it. It'll be an inverse relation, not an inverse function. Algebraically then, as we said, well, x will be y squared, but we get plus or minus. So it's not unique. There's two possibilities there. Not an inverse function. As opposed to, say, the cubic, vertical line test, beautiful, it's a function. Horizontal line test, again, no matter where I put that horizontal line, it'll satisfy that rule. So yes, it does have an inverse function. Algebraically, swap them, x equals y cubed. So y is the cube root of x, and if we're dealing with real numbers, there is only one cube root of x. So it is unique, so it has an inverse function. So 5F is on inverse relations.